Okay, in the last video we were talking about expected value in odds, and I went through an example of expected value, and I said for this one I was going to go through another expected value type problem that's similar to the ones you'll see on this lab worksheet that I have for you and on your homework and all that. So what we're going to do is kind of like a game of chance. Suppose I go to a carnival and I play a game. And here's the rule. Let's see. It costs $1 to play. And what I do is I roll a die. Make this relatively easy. If I roll a 1 or 3, I get $1. If I roll a 2, a 4, or a 6, I get $2. Actually, we'll just say if I roll a 2 or a 4, I get $2. If I roll a 5, I get 0. And if I roll a 6, I get $5. So I have this game right here. I roll a die, there's 6 possible outcomes. Here's all the different results based on what I roll. Should I play this game? Is this a good game for me or a bad game for me? One of the ways we figure that out in math is by way of expectation. And, well, the expected value will give me an idea of what I can expect to happen as I play. And the way we interpret it in math, well, if my expected value is positive, that means I can expect to make money. So I should play. If my expected value is negative, then I can expect to lose money. I shouldn't play. If my expected value is 0, it's what's called a fair game, meaning I don't expect to win or lose, so it doesn't actually matter if I play or not. Want to play for fun? I can. If I don't want to waste my time, I don't have to. Ultimately, a lot of the games we play are designed to be fair, but in actuality, that doesn't make the games fun, meaning if there's no chance for me to win something, then I'm really just wasting my time. So there's actually, from a mathematical perspective, this interesting thing where what we call fair, we would actually also call boring, because there's no expectation that I'll win anything over time. But that, I'm not sure how deeply you're going to go into that in your 143 class, so I'll stop there. But suppose we have this experiment, this game right here. I want to find the expected value, so I know if I should play or not. So, first thing I do is I list out my outcomes. And here, keep in mind, it's the outcomes for this experiment. In this case, there are 4 outcomes. I know there's 6 rolls, but there's 4 outcomes right here. We'll just call them 1, 2, 3, and 4. For my first outcome, well, let's see, I get $1. So maybe we'll list my probability first for this one. So we'll do probability and then outcomes. That might make this easier to see, and I'm trying to make this as clear as possible. So for the first outcome, what's the probability I roll a 1 or a 3? That's 2 out of 6. The second outcome, what's the probability I roll a 2 out of 4? That's 2 out of 6. What's the probability I roll a 5? 1 out of 6. What's the probability I roll a 6? 1 out of 6. Like we said last time, we check to make sure my probabilities add up to 1. 2 6 plus 2 6 plus 1 6 plus 1 6 is 6 6. That's 1, so we're good. Now I need the outcome, which is what happens when this thing happens. Here, what happens when I roll a 1 or a 3? But we have to be careful here. When I roll a 1 or a 3, I get $1. So what do I actually win? 0. Because I get $1 for rolling 1 or 3, but it costs me $1 to play. Which means the net result, I paid $1 to play, I won $1 during the game, I ended up getting 0. So keep that in mind. If the game is free, then you would just use these outcomes. Since the game is not free, you have to factor in the price to play. So for the second one, if I roll a 2 or a 4, probability 2/6, I get $2, but it cost me $1 to play, so I actually ended up winning $1. Third outcome, roll a 5, that's 1 out of 6. I get 0, so I don't win anything, and it cost me $1 to play, which means I actually lose $1. Lastly, to roll a 6, probability 1 out of 6, I get $5, it cost me $1 to play, so I actually end up winning $4 total. Now, I have my probabilities and I have my outcomes. I multiply. (2/6) times 0 is 0. 2/6 times 1 is 2/6. 1/6 times -1 is -1/6. 1/6 times 4 is 4/6. Now, I add up this column. 4/6 plus 2/6 is 6/6, minus 1/6 is 5/6. The 0 doesn't matter. So my expected value is 5/6. Keep in mind this is money in terms of dollars. So this is 5/6 of $1, or 0.83 cents. For 83 cents. So what's my expected value? 83 cents. What does that mean? Should I play the game? My expected value is positive, which means in the long run, I can expect to win. Again, like we said last time, does that mean that when I play, I win 83 cents? No, I can't win 83 cents. I win $1, $2, 0, or 5, and then it gets altered because of the price to play. But what the expected value is saying is, if I play this game over and over and over and over, each time I play, I can expect to win about 83 cents. So maybe if we say it this way. If I play 10 times, what should happen? If I play 10 times, I can expect to win about 83 cents per game. So in 10 games, 0.83 times 10, that's $8.30. So if I play 10 times, I can expect to win about $8.30. Again, I never win $8.30, but what that tells me is, the more I play, it seems like the more I'll win, because my expected value is positive. If I play 100 times, win 83 cents per game times 100 games, that's $83. And again, what this is saying is, the more I play, the more I can expect to win. So should I play? Yes. If this expected value was negative, like if this was set up slightly differently and this was negative, then it would say, the more I play, the more I can expect to lose, I should not play. Ultimately, again, we have what's called a fair game in math. A fair game means your expected value is equal to 0. You neither win nor lose. The problem is, again, if you never win or lose, then really what's the point of playing? And you're kind of stuck in this catch-22, where you want to play a game where you can win, but think about it. If I'm playing a game where the expected value is positive, I'm winning, it means the person running the game is losing. Their expected value would be negative, which doesn't seem very fair, and they really wouldn't want me to play it, because me playing makes them lose. But on the other hand, if my expected value is negative, that means the dealer's expected value is positive. They want me to play, their expected value is positive, but I don't want to play because my expected value is negative. Which means the only time that it really works is when the expected value is 0. It's fair because I don't win or lose, and the dealer, person running the game, doesn't win or lose. But then frankly, does anybody really want to play? Because nobody wins or loses. So there's the math of what's going on, there's the understanding of what the expected value is and how to find it, find the probabilities of all outcomes, make sure they add up to 1 to make sure you've accounted for everything. Find the actual outcome, account for the price to play and things like that. Multiply across, add up, get an answer. Then there is the interpretation. Positive expected value, negative expected value, what does it mean? Should you play? Is it fair? All of those things. All of you know by this point, yes, you do math type questions which you solve. There's also the interpretive aspect of what you're doing, understanding what the math means and what's going on. So make sure to keep that in mind. These examples should give you enough to go on with expected value. But again, I'm aware that expected value, even with this simple formula, can get a little bit tricky to set up and understand sometimes. So again, if there's more questions, feel free to email me, ask me, and I'll make even more videos going through more examples of this.